Hi, this is Phil Koopman with a tutorial on embedded software requirements. As we go over different parts of the software development cycle, we'll eventually hit all the boxes in the V process model. This tutorial covers requirements, both product requirements and software requirements. Let's start with an overview of the topic of software requirements. We'll be emphasizing embedded software requirements issues, but in general, the topics we'll talk about apply to all software systems. Some anti-patterns for software requirements are, if your requirements are not written down, that will cause problems. Another anti-pattern is if you have incomplete or imprecise requirements. Another anti-pattern is the requirements exist, but they all look like, be just like the last version except do this thing, which leaves you without baseline requirements. Requirements are essential to a successful software project. Requirements faults, missing requirements, defective requirements can defeat a design before it's even built. Requirements are there to describe what the system does, and especially for mission-critical systems, requirements also need to say what's not supposed to happen. They need to use precise, testable language, and ideally, every requirement traces to a system test that's designed to make sure that requirement was actually fulfilled. It's commonly said that many, if not most, major software failures trace back to bad requirements. By the time you have a big software development disaster and project failure, there's usually plenty of blame to go around. But an example of a time when it was clear that requirements really contributed to a big software failure is the FBI Virtual Case Project. Approximately $170 million were wasted on this project that never was completed and was thrown away in favor of a new project in 2005. The idea was to automate the handling of all the files for the FBI. And right out of the gate, the project had problems. Starting with, requirements were not actually defined when the development contract was signed. So apparently they signed a contract saying build us some software, but the contract did not say what the software was supposed to do. That should have been a red flag right there. Early on, it was said that the requirements amounted to, give it a try, we'll know it when we see it. While that approach might be good for requirements elicitation and early exploration, it's not a sound basis for developing a major piece of software in the middle of the project. Unsurprisingly, there were repeated requirements changes. Some of them were from we'll know it when we see it, but others were because they had not considered all the different users of the system, and it turned out that different users had significantly different requirements. In the end, they had scope creep, which is new requirements being added, of 80%. A number of other things went wrong, and eventually they pulled the plug on the project. The takeaway here is that if you don't have reasonable requirements at the beginning of a project, it's probably going to be downhill from there. To be clear, you're unlikely to have perfect, absolutely complete requirements on day one. But if you do not have a reasonable starting point, the project is going to have problems. Good requirements tend to have some common characteristics. An important attribute of good requirements is that they are both precise and minimally constrained. By minimally constrained, we mean that they describe what the system should do, but not how the system does it. The how it does it is part of design, not requirements. Part of being precise is that a typical requirement uses the word shall as its verb to require that something happens, or sometimes the word should to state a goal. So if you have a properly formed requirement, typically the verb is going to be either shall or should. Another good, precise requirements practice is to have a numeric target instead of a qualitative term. For example, instead of saying the user interface is fast, you might say that there's a response to a user selection within 500 milliseconds, or the period for a refresh is 500 milliseconds plus or minus 10%. Using a tolerance is important rather than a precise number to indicate the degree of freedom that designers have in meeting a timing target. A good requirement should be traceable and testable. Each requirement needs a unique label, for example, R-7.3. That label makes it easy to trace the requirement to an acceptance test. In your acceptance test plan, rather than have a complete repeat of the text of the requirement, you can just say, this test checks requirement R-7.3, and you know exactly what the test is for. Each requirement should have a feasible yes-no test. At some point, if you have a requirement, you want to know whether the system actually does it or not. If it's something you cannot test for, that makes it a problem knowing whether your system does what it's required to do. What you'd like to see is that each use case in the system translates to one or more requirements, and those requirements are linked up to tests to make sure that the requirements are actually met. The requirement also needs to be supported within the context of the system. You might say that a particular function has to happen, that's the requirement, but it is often useful to have a rationale or a commentary explaining, now what exactly did we mean by that? Why is this important? How does it interact? The commentary is part of the requirements document, but the requirement should stand alone as long as you understand the background information. Requirements should use consistent terminology. Anytime you use two different words, that raises the question, now did you mean the same thing by those two different words, or are they different things? So a good set of requirements uses the same word to mean the same thing throughout. It's difficult to create a large set of requirements with no conflicts whatsoever. Typically there are conflicts, and the requirement should provide advice on how to resolve or prioritize the conflicts. Just because a requirement has the word shall in it does not automatically make it a great requirement. There are a number of different problems with the requirements. One example is a sign coming out of a tunnel while you're driving saying, "Headlights on?" That sign is a prompt, a requirement to the driver that says, do the right thing with your headlights. It turns out that doing the right thing with your headlights is pretty complicated. Is it day? Is it night? Is it foggy? Is it raining? And so on. This prompt is also a little ambiguous because different drivers might have different ideas of what doing the right thing means. The types of problems you typically see in requirements include the following. A requirement may be untraceable. There's no label. System shall shut down when e-stop is activated. There's no label, so there's no nickname to use in tracing it to see if there's really a system test. That means the requirement text itself might be okay, but in the context of a software process, there's a piece missing. A requirement may be untestable, R1-1.1. The software system shall never crash. Well, that's nice, but how exactly do you test it? Do you have to run it for an infinite amount of time to see if there's a software crash? That doesn't sound viable. A requirement may be imprecise. In this case, R1.7, the system provides quick feedback to the user. How quick is quick? 300 milliseconds? 100 milliseconds? 1 nanosecond? At some point, there's a boundary below which being faster doesn't really help. Requirements might not have a measurement tolerance. R2.3, LED shall flash with a period of 500 milliseconds. Well, is that 500 milliseconds plus or minus 10 milliseconds? Or is it 500 milliseconds plus or minus 1 nanosecond, which means you have to have hardware to implement it? If there's a margin for timing, it's important that it show up in the requirements. Requirements might be too complex, and I'm not even going to try and read this one. Requirements should be broken down to single statements of some situation is happening, some part of the system does some action. This requirement should be broken down into multiple requirements. Another problematic requirement is one that describes an implementation. Pressing button W shall cause two 16-bit integer values to be added. That's not a requirement. That's a verbal sketch of an algorithm. Requirements should stay away from implementation and just describe what is supposed to happen and let the designers deal with how to make that happen. Requirements are often written in natural languages, such as in English. Natural language requirements are prone to ambiguity. No matter how hard the requirements writer might try, there'll always be a little ambiguity. And part of the skill of a good requirements writer is to be creative in thinking about potential ambiguity, even from somebody who's trying to honestly understand what the requirement means. A joke to this point is, a requirements engineer gets a text message. On the way home, please pick up 1 carton of milk. Well, the requirements engineer is already thinking this is a problem. Is this a quart, a half gallon, or a gallon? But the requirements engineer knows that usually they buy half gallons, so go with the half gallon. But there's another part of the text. And if they have eggs, get 6. Okay, medium eggs, large eggs, brown eggs, white eggs. Okay, but got it. The requirements engineer comes home with 6 cartons of milk and no eggs. The spouse says, "Why did you buy 6 cartons of milk?" And the requirements engineer replies, "Well, they had eggs." Not all requirements deal with what the product is supposed to do. Extra functional requirements, sometimes called non-functional requirements, deal with things that are other than lines of code that cause something to happen. One set of extra functional requirements is emergent properties, things that are hard to allocate to a single component. In a classical airplane, there's no one component that makes the airplane fly. It's an emergent property of all the different pieces working together. Some airships actually have a make-us-fly bag of helium, but that's the exception, not the rule. Emergent properties include performance, things like ability to meet real-time deadlines, security, safety, and dependability at the system level in general, size, weight, and power consumption, often called SWAP, with these emergent properties often being handled via having budgets that are allocated a little piece of each size, weight, and power budget to each component. There are often forbidden behaviors. The system shall not do something. Well, in general, there's no line of code that prevents you from doing something you're not supposed to do. Rather, that's an emergent property that all the lines of code when put together do not display that behavior. This is often in the context of safety requirements. There is a trick you can use here called a safety function, which monitors for the bad thing happening and then takes a corrective action. But the bad thing trying to happen in the first place is an emergent behavior. Another type of extra functional requirement is a design constraint. The design must meet one or more different standards. The design must use a particular technology. The code has to be written in a particular programming language, might be a requirement for legacy and compatibility reasons. Another design constraint might be the total system cost or a project deadline or project staffing. All of these things are real requirements that apply to real systems, but none of them have to do with writing a line of code that does a certain thing. These should all be addressed by the requirements document one way or another. In the You Are Here slide, requirements hit 2 boxes in the V: product requirements and software requirements. In some cases, there are 3 levels of requirements or more depending on how the system is decomposed. But generically, there are 2 types of requirements. One is from the product point of view, the other is a detailed engineering point of view. The product level requirements talk about what the product does, typically from the way a user sees the system. As an example, PR6, product requirement number 6. The clock shall support a user-settable audible alarm. That does not tell you what the alarm sounds like. It's not even clear what user-settable means. But from a product definition point of view, it means that there has to be an alarm and the user has to be able to say what time the alarm should activate. Product level requirements typically look like a feature list of what the product does that a user or purchaser of the product would be interested in. Product requirements ideally are the interface between marketing and engineering. The marketing group says this is what we want to sell, and the engineers use that as a starting point to figure out what to build and how to build it. More detailed engineering requirements talk about how the product actually works. For example, R5, time set buttons shall change the alarm set time. Much more concrete, it tells you how the system works. Embedded systems also have detailed requirements that may be tied to operational modes. For example, R5, in alarm set mode, the time set buttons shall change the alarm set time. That implies there might be other modes, such as the setting the time of day mode, but that's not this requirement. R6, pressing the plus time set button shall increase time value by 1 minute per button press according to the current set mode. That's a very specific requirement that tells you exactly how setting the time works, whereas the product requirements just say the function has to be in there someplace. There are a number of different approaches to requirements, and all of them have their place and use. Sometimes requirements are a text document that just lists a bunch of things using shall sentences. This works best if the development team is full of domain experts who already know pretty much what's going on, and they just need a written list to make sure they keep it straight. Over time, a text document can converge to reasonably useful requirements, but if somebody walks up with a brand new product that's never been built before and shows you a 1,000-page set of requirements, you can expect that it will be difficult and problematic to go through it and get everything straight. An alternate approach that can help organize and explore requirements on a newer system is the use of Unified Modeling Language (UML) use cases. A use case diagram shown includes the actors, in this case a customer, but they can be others, and a number of interactions that they have with the system. So for a soda soft drink vending machine, the customer might insert money, they might select a soda by pressing a button, they might want their money back, they may want to know if a particular type of soda is in stock, and so on. Each of these use cases serves as the basis to create more detailed requirements. But in a single picture, you can see all the ways that a customer can interact with the machine, and that's very helpful for exploring requirements, making sure there's no missing requirements, and so on. Each use case has one or more scenarios that have more detailed interactions. For Agile teams, user stories are generally the way that requirements are described. Each user story describes a system interaction. An alternate way, more commonly used in aerospace and government projects, is functional decomposition. In functional decomposition, the team starts with a list of the primary system functions. For example, a car might have the primary system functions including being able to move, being able to change direction, being able to load and unload passengers or cargo, and so on. Underneath those primary system functions are more and more detailed lists of sub-functions, creating a functional architecture. This approach is often used when there are chunks of hardware and software that are obtained from different vendors, and the functional decomposition organizes which chunks the system is broken down into to subdivide the work up into different teams. There is a role to be played in prototyping with requirement solicitation. If you're building a new product, you probably do not know all the requirements up front. That does not mean dive into writing code. That means you have to do something to describe the requirements. On the first day, you might say the customers will know it when they see it. Well, okay, that may be true, but it's not time to start writing software. It's time to do paper mock-ups, focus groups, and so on, to try and get an idea of what system you're actually trying to build. Once you can distill that into at least a first set of requirements, then it's time to start developing, but not before. Rather than staring at a blank sheet of paper, it can be better to use a template-driven approach to writing requirements. One such approach is the easy approach to requirement syntax, EARS. In this approach, there is a standard template for all requirements, and that template is a while or where of some precondition, and possibly a when or if of a trigger, leads to the system shall response. There are a number of specific templates within that general pattern. One is the ubiquitous template. The touch screen shall have a response time of less than 250 milliseconds. This is a situation which has to always be true for the system. The state-driven requirement template is while an external speaker is connected, the internal speaker shall mute. So state-driven is some condition that is true, and the entire time that condition is true, some requirement must be fulfilled. But when that condition turns false, then the requirement no longer applies. The event-driven template is when a card is inserted, the card reader shall verify credentials. This is an action triggered by an event, and the requirement has to have some sort of response that happens one time when the precondition is met. There's the optional feature pattern, where a convertible roof is installed, a park roof motion interlock function shall be provided. Rationale: that way the roof doesn't tear off when the car starts driving down the street. In this case, the where keyword is intended to mean there's a feature or component that might or might not be in the system, but if it's there, this requirement applies. There's the unwanted functionality template. If an invalid value is entered, then an error message shall be displayed. This is intended to provide exception handling and error handling. The complex template isn't really a template, it just permits the ability to mix and match the templates above for things that have to be more complicated. To be sure, you want to boil down requirements to the simplest possible form, but sometimes things are a little more complicated than the templates above. The ears work also has an interesting list of requirements issues, things that can be wrong with a requirement that's worth a quick look. The attributes of requirements they found problematic are requirements that are ambiguous, vague, complex, omitted or missing, duplicated, wordy, describe an implementation, or are untestable. Here are some example requirements from a NASA requirements document. Going across the columns from left to right, we can see there's a parent requirement, which is going to be a product requirement. And that product requirement results in one or more software requirements, the rec ID. In this case, the top row is SRS, Software Requirements Specification 3.2.6.12. That means there's a lot of requirements here. And the next column is Requirements Text and Rationale. The software shall send data at a user data rate from 0 up to and including 100 megabits per second. Below that is a rationale explaining why that requirement is important and what it does. The column after that is a priority, though some requirements will have higher priorities than others. And the last column is an allocation, and that is which subsystem or which functional block is this requirement allocated to, meaning that that subsystem is entirely responsible for the ability of the overall system to meet this requirement. Summing up, here are best practices for embedded software requirements. Requirements engineers often talk about the 6 C's for good requirements. A good requirement is clear, concise, correct, coherent, complete, and confirmable. Also, a good set of requirements deals with extra functional issues and relates the requirements to the design flow, going back up to user stories and product requirements, but also across the V to figure out which tests actually test to make sure the requirement has been met. Some requirements pitfalls include the following. It's important to avoid unnecessary details in implementation to avoid making the designer's job too difficult. It's important to remember that if it's missing from the requirements, it won't get done. The requirements have to have everything the product needs to do. Also, if you have a requirement that's not testable, you will not know if it got done. And finally, it's important for requirements engineers to have a little humility because you will not think of everything. You need to do the best you can and then improve the requirements over the life of the project. For example, a vehicle headlight designer might not have thought about what it means to do the right thing during a total solar eclipse.